shoot an arrow at a wall of gelatin and you would expect it to pass right on through. Imagine your shock, however, if the arrow suddenly flew back at you.
Okay then, new game.
But that is exactly the kind of shock physicist Ernest Rutherford received when he tried to penetrate atoms with something even smaller, alpha particles.
Goodness!
In 1897, J.J. Thomson had theorized that atoms were similar to positively charged gelatin, with negatively charged electrons sprinkled around like bits of fruit. According to that theory, Rutherford's alpha particles should have punched straight through that flimsy atomic gelatin. And most of the time they did. But to Rutherford's surprise, a small number of alpha particles were deflected right back in the direction they came from.
Crikey, they must be hitting something a lot harder than gelatin.
Rutherford realized the atom must be comprised mostly of empty space, with an incredibly dense, positively charged core or nucleus.
Hey, there's a marble in this gelatin.
His student, a Danish soccer jock by the name of Niels Bohr, carried the ball a bit further. He proposed that the atom looked like a miniature solar system, with a dense center around which the electrons orbited.
But things got a bit sticky when I tried to explain why the orbiting strawberries, electrons, didn't lose energy and eventually collapse into the nucleus. That's what Newtonian physics would have predicted.
But modern scientists like Max Planck had rewritten some rules, showing that things like energy and light are not continuous streams.
No.
Instead, they are made up of individual packets of energy, called quanta. He even came up with a way to describe the size of these quanta, a formula known as Planck's constant. Bohr's atomic model would need some new rules as well. Bohr put Planck's constant to work, poring over his calculations day and night, probably to the distress of his fiancée. Their wedding was just a few months off.
Almost there.
Yes, time to pick out our China pattern.
Almost done, my little peach Danish. I postulated that as long as an electron remains in any of several stable orbits, it will not emit radiation nor lose any of its energy. I do.
Eureka! Bohr had unlocked a critical mystery about the nature of matter itself. What gives elements like gold
and helium
their unique properties. Bohr understood that an element's chemical properties were related to how nearly empty or full the outer orbit or shell was. Lithium, hydrogen, and sodium, for instance, all have one spare electron, which allows each of them to bond with chlorine, a fellow in dire need of a single electron to complete his outer orbit.
Here, take one of my electrons. I don't need it. Why, thank you.
When two or more atoms share electrons that complete their respective outer orbits, they form stable molecules. For his work boring deeper into the atom's mysteries than anyone before, Niels Bohr received the Nobel Prize for Physics in 1922.